Welcome to the Explainer. Today, we're pulling back the curtain on a hidden science that pretty much makes our modern world work: sensor calibration. It's this crucial behind-the-scenes process that makes sure all the tech we rely on every single day is giving us the real story.
I mean, think about it for a second. That temperature on your thermostat, the speed on your car's dashboard, the weight that pops up on a digital scale. We trust these numbers, right? We take them as fact. But should we? How do we really know our devices are telling us the truth?
Well, here's the thing. No sensor is perfect. Not a single one. From the very moment it's made and all through its life, every sensor has this natural tendency to drift away from giving a perfect, accurate reading. Their measurements can get a little bit off. Quietly, slowly, but surely.
So why does this happen? Well, it comes down to a few key things. You've got these tiny imperfections from the manufacturing process itself. Then there are environmental factors, changes in heat or humidity. The components inside just get old like anything else. And then there's just that slow, gradual drift that happens over time. All these things are constantly working to push a sensor off its mark.
Okay, so we've got this problem of our sensors getting inaccurate. But don't worry, there's a really powerful solution that brings our measurements back down to earth, back to reality. And that's what we're going to get into now: sensor calibration.
At its heart, calibration is basically a reality check. It's the process of taking a sensor and comparing what it says to what a super accurate, trusted standard says. The whole point is to find out if there's a difference, an error, and then, of course, to correct it.
And the guiding principle here is beautifully simple. The error is just the difference between the number your sensor is showing you, the measured value, and the actual real number, the true value. That little difference, that's the number we need to fix. So finding that error is basically a four-step dance. First, you give the sensor a known input, like a perfectly controlled temperature. Second, you see what the sensor says. You measure its output. Third, you compare that reading to the real value. And finally, number 4, you use that difference to adjust all the sensor's future readings so they're accurate.
Right, but it's not like there's just one way to do this. Calibration isn't a one-size-fits-all kind of deal. Depending on the sensor and what it's being used for, engineers have a few different methods to get the job done right.
The two big ones are direct and indirect calibration. Direct is exactly what it sounds like. It's simple, super accurate. You compare your sensor directly to a gold standard reference. Think about checking a new kitchen thermometer against a super precise lab one. Indirect is what you use when creating that perfect input is tough. So instead, you just compare your sensor against another sensor that you already know has been perfectly calibrated.
Then there's another way to slice it: timing. Are you measuring something that's staying still or changing like crazy? Static calibration is when you test under steady, constant conditions, like slowly increasing the pressure on a sensor. Dynamic calibration is the opposite. It's all about testing how well a sensor can keep up with rapid changes, like a sudden spike in temperature.
So, you've done all these tests, and now you have a whole bunch of data. What do you do with it? How do you make sense of it all? Well, the key is to visualize it on something called a calibration curve.
This graph tells the whole story. On the bottom, you have the true value, and on the side, you have what your sensor measured. Now, in a perfect world, this graph would be a perfect, straight, diagonal line. But, in the real world, that almost never happens.
So let's break down the common errors this curve can show us. First up is an offset error. The best way to think of this is a scale that says you weigh 1 kilogram before you even step on it. That's an offset. The sensor is consistently off by the exact same amount, no matter what it's measuring. Next, you've got a sensitivity, or gain, error. This one is all about the slope of that line being wrong. So for every 1 degree the temperature actually changes, your sensor might say it's changing by, say, 1.1 degrees. The error actually gets bigger as the measurement gets bigger. Then there's nonlinearity. This is when the sensor's response isn't a straight line at all, it's curvy. It might be accurate at low temperatures, way off in the middle, and then sort of accurate again at high temperatures. It's an unpredictable error that changes all over the place.
And finally, one of my favorites, hysteresis. This one is really fascinating. It's like the sensor has a memory. It gives you one reading when the temperature is rising, but a totally different reading for the exact same temperature when it's falling.
Okay, so we've been deep in the technical details here, but let's pull way back for a second. Why does any of this actually matter? What's the real-world impact of all this stuff?
Well, at the end of the day, proper calibration is the foundation of our trust in technology.
It's what gives us accuracy, what ensures that one device is consistent with another, and it's absolutely vital for quality control in manufacturing. It can even prevent really dangerous errors in complex systems, like an airplane's autopilot.
And you see its importance everywhere. In factory robots that need to place parts with pinpoint precision, in scientific instruments monitoring climate change, in the medical devices that keep people safe. In all of these, accurate calibration is completely non-negotiable. It's the bedrock of reliable performance.
You know, the source material we've been digging into really puts it perfectly. It says that calibration isn't just a good idea, it is essential for maintaining the accuracy and reliability of our measurement systems, period.
So, I'll leave you with this one final thought to chew on. What if nothing was calibrated? Just imagine a world where the fuel gauge in your car is just a guess, where your oven's temperature is never quite what you set it to, where every scientific experiment is built on a foundation of completely flawed data. It really makes you appreciate this invisible process, working tirelessly in the background to keep our world in focus.